Cool. Uh, so this is lecture 19, where we're going to start this new topic, which is extractors. Uh, so today's class is going to be an introduction. So it's going to basically give you a sense of what extractors are, how it's useful, and so on. And in the next, my guess is about 4 or 5 classes, we will actually work towards building them. But today it's just going to be to give you the relevance of extractors in the field of pseudorandomness. Uh, so far things that we had done was more like reducing the amount of random bits. So either we wanted to get rid of random bits completely, which is roughly what we were trying to do in the PRG setting. But maybe like the previous settings, etc., when there were samplers and so on, it was more like there was a way of achieving certain goals using a certain amount of randomness. And we were trying to get roughly the same goal with using far less randomness or something. And we had different notions of efficiency, maybe based on the number of random bits you used or the number of samples you needed, etc., etc. And depending on the context you're working with, one of these settings might be more relevant. So today's lecture is going to be, or rather this module is going to be on a slightly different setup, where we basically say, okay, fine. We often design algorithms where it takes some random bits so that it can answer some interesting yes/no question on a certain input X. Okay, so we have some randomized algorithm where the input provided is X, but in the course of the randomized algorithm, I might be using some random bits to eventually decide whether the answer is yes or no, with some where the error is like quite small. And the important thing to note is that in many applications, you assume that the random bits that you use is like uniformly random. Okay, that's sort of, we don't think too much about this, but maybe let's ask ourselves, how are these, like when these things are implemented in practice, like when someone writes I don't know, library for something or whatever, like where do we get these random bits from? And honestly speaking, we don't really get these uniformly random bits. But what instead is usually done is there is usually called a random number generator or something, which takes a whole bunch of sources. Like for instance, it might take something like your mouse movement. Uh, in fact, some of these, like if you have run this SSH key generation algorithms or something, sometimes it might explicitly ask you to type random stuff on your keyboard. Just mash your keys or something. So keyboard input. Sometimes it will take things like whatever, some system clock or whatever. So it takes a bunch of these, what do you call them? Like some sources which have some inherent amount of randomness in them. And it might also be that some of these sources are correlated with each other. And it takes all of this and tries to produce something that sort of looks random. Okay. And the hope is that you feed this guy into the algorithm, and hopefully, the algorithm guarantees don't change too much. Like you get the rough qualitative guarantees. Like maybe you're off by a small epsilon or something, and as usual, if your gap that you could tolerate was something like 1/3, then an epsilon being something like 1/10 or something is not going to hurt you much. And that's the rough idea. This is actually what is typically done in practice. They will take a whole bunch of like quasi-random sources or something of that sort, some weird sources, and just somehow mash all of these bits together to produce a few bits which you believe is unbiased and uncorrelated. In some sense, that is morally speaking is the case. And this is really what extractors are. Okay, what extractors are basically, it's some efficient way of extracting pure randomness or close to pure randomness from what are called impure sources in some efficient fashion. So there are obviously, this is a very informal definition, and there are a lot of things that are unsaid here, which is what do we mean by extracting randomness? What do we mean by close to random? What do we mean by impure sources, etc., etc. And today's lecture, what is going to happen is we're going to try and come up with suitable definitions for them. Some of them may work, some of them may not work. And so that it slowly guides us towards the main object we are going to study for the next about 4 or 5 lectures. Okay, so that's going to be the thing. So unlike the previous modules, we are not really trying to reduce the amount of randomness per se, but we are basically trying to make, I mean, like, live in this more realistic world where randomness may not be pure randomness, but I would still want to use it for my algorithms. My algorithms often depend on pure randomness, but can I still make those algorithms work? That's what we are going to focus on in this module. Okay, so in some sense, what an extractor is, in a slightly more formal sense, is the following. It's some function that takes a sample from a certain distribution X. So X is some random variable which returns, I don't know, strings of a certain length or whatever. And we want to somehow take one such sample and convert it to some Boolean string of M length Boolean string. Okay, and this X is going to be some impure source which we will try and make precise in some time. But we'll start off with certain examples and try to then come up with a definition for it. But okay, but just think of any of these things, like you have your mouse movements or keyboard input or system clock or whatever, and you take all of that, and then you want to, at the end of the day, return a string such that the distribution of the output of the extractor, when X is chosen according to your distribution, whatever is the weak random source that you have, that must look like the uniform distribution. Okay, what do we mean by look like the uniform distribution? Normally, this error is measured based on this total variation distance, which we briefly discussed earlier, but I'm just going to formally define what total variation distance is. Total variation distance is some measure to sort of get a sense of how close are two distributions. Okay, and the formal definition is this, but I somehow think the pictorial way of describing it is maybe it's easier to keep in mind. So think of this is the so the x-axis is basically all the points in your sample space, and the y-axis is the probability. Okay, so each of them, I mean, like maybe this is the distribution corresponding to X, and maybe this is the distribution corresponding to Y. Okay, and in some sense, the total variation distance basically tells you what is this gap. Okay, maybe up to a factor of 2 or something like that. So sort of giving you a sense of, if you look at these two, the graphs of the distributions in some sense, what is how much gap is there? And as you can imagine, the smaller this gap is, it roughly tries to tell you that these two distributions look a lot similar. I mean, in the sense that the probabilities don't seem to differ by much, etc. So this is one definition, but total variation distance is a very, very important concept. I mean, and it has a lot of very nice properties. This to me is perhaps the most important property of total variation distance, which is it actually tells you that no matter what test function you take, as long as the range of the test function is bounded between -1 and 1. So any test function that you take, the expected behavior of the test function on the distribution X and the expected behavior of the test function on the distribution Y can differ by at most the total variation distance between X and Y. So it gives you a way of saying that if the total variation distance is at most epsilon, then from every test's point of view, the distribution X and the distribution Y look identical. Or rather, up to a small epsilon change or something, they look more or less the same. Okay, so this is like the PRG setting. Normally, in the PRG setting, we will sort of say we are only interested in efficient algorithms A as our test functions or something, but total variation distance is completely oblivious to any of these computational sort of constraints. It just says this is the guarantee I can give you on any damn test function you have to try and distinguish X and Y. Okay. By the way, this is often also written as you think of just A as going from sigma to just the set 0, 1. That is, think of A as being an event of whether the corresponding sample lies in this set A or lies in this event or not. And this is just a convex combination version of the same thing. Just okay, but they're basically identical. Okay, so this is one sort of useful perspective to have when it comes to total variation distance. There's also another very nice perspective, which is in some sense the dual version of this total variation distance. I mean, it's written too tersely. There is a lot of mathematical symbols, but let me try to break this down. So basically, what this says is try and find a distribution pi on pairs, okay, such that the marginal on the first distribution looks like the first coordinate looks like x, and the marginal on the second coordinate looks like y. Okay, so that's what I'm minimizing over. So that's this big, that's this inf there. And you ask, okay, there are many possible such joint distributions you could have constructed where the first coordinate alone looks like x, the second coordinate alone looks like y, but maybe there are some correlations between the two coordinates. Okay, what is the smallest you can make the probability of x, the first coordinate, not equal to the second coordinate? Okay, and that's a different way of saying what total variation distance is, because this smallest value turns out to be the total variation distance. So distributions where the two coordinates independent, I mean, like on just if you focus on just coordinate 1 or coordinate 2, it looks like x or y. These things are called couplings. So you basically say among all possible couplings of x and y, what's the smallest you can make the probability x not equal to y? Okay, and that's the dual form of total variation distance. This is also very useful in many other contexts. And if you want to get a sense of this, think of x as being the distribution which is the Bernoulli with probability p. That is, it's just 0, 1, but it's like it takes value 1 with probability p. This guy is, let's say, Bernoulli with probability q. Okay, and you can try and figure out what the total variation distance between these two is, and try and figure out what the right coupling is. It's quite an instructive exercise if you haven't seen this before. But we won't really need any of this much, but it's just a useful sort of fact to keep in mind. But here are some very simple to verify properties, at least to give you a sense that this total variation distance seems to be a very useful definition. Okay, so the first, I'm not going to prove any of them, but hopefully they all should seem very natural or obvious to you. The first one is that the total variation distance is always some number between 0 and 1. This should be obvious. And in fact, it is equal to 0 if and only if x and y are exactly the same distribution. Okay. And secondly, it satisfies the triangle inequality, which is that if you look at the distance between x and y and the distance between y and z, and you add them up, that's certainly at least as large as the distance between x and z directly. So this is just triangle inequality. And this, I don't know, I mean, maybe this is something like a data processing inequality or something, which basically says that if you have two distributions x and y, and you decide to apply some function f on both of them, now after you apply the function f, they can only get closer. I mean, in some sense, you might just be losing some information, some granularity that you knew about x and y as a result of applying the function. So if you process your random variable and then look at that the resulting distribution, the distribution can at most be, I mean, the distance will be smaller than what you started off. That's what the third bullet roughly says. And the fourth bullet is basically saying that it behaves in an additive fashion as long as the different coordinates are independent. That is, if you're thinking of a joint distribution x1, x2 and comparing it with another joint distribution y1, y2, where you are told that x1 and x2 are independent and y1 and y2 are independent, then that should basically be the distance between the first coordinates and the distance between the second coordinates. Okay, so that's so all of this hopefully seem fairly natural to you. You don't need to really verify these or something, but as long as you're convinced of this, it's fine. So Abhishek, you had a question?
Yeah, so did you mean an equality here rather than an inequality in the
last?
Oh,
sorry. I meant equality here.
Yeah. Okay.
Yeah, I mean, in the sense that it's additive, in the sense that if things are independent across coordinates, then you might as well add up the total variation distances across coordinates.
Mm-hmm.
Yeah. Thanks. Okay, so that's going to be our notion of closeness. So when we were talking about extractors, we wanted to say that I want the output of the extractor to look like the uniform distribution. And What do I mean by look like? Well, I mean look like in the sense of total variation distance. I'm going to have a tolerance parameter epsilon like we had in PRGs and say that I want my guarantee output to look epsilon. It must have total variation distance at most epsilon with respect to the relevant uniform distribution. Okay, good. So now let's ask ourselves, suppose such an extractor existed, like these sort of functions, something that takes an impure source and then returns some 0, 1 to the other. But we still haven't even defined what impure sources mean. But let's just, before we dive too deep into this, let's at least convince ourselves that what we are doing has some Swiss worthwhile. Okay. So suppose we did have such a thing, and now I have a randomized algorithm which I want to run, but the only thing I have in mind, I have at hand is some impure source. Okay. But somebody told us that, oh, by the way, here is an extractor for this impure source. It seems to do reasonably well. So let's ask ourselves, suppose we have this impure source and an extractor, can we still use it for randomized algorithms? Okay. So what would we do in this point? In such a situation?
Sorry, what are we asking? Can you repeat?
So we are just saying that, I give you an impure source. You have access to some impure source X. And you have access to an extractor. That is from X to 0, 1 to the M or something. Okay. And I have a randomized algorithm A, which required M random bits, like truly random bits. So now but I don't have access to pure randomness. I only have access to these extractors.
Yeah, so we can sort of use X and then extract.
Yeah, so let's say this is my randomized algorithm. I needed to feed in random bits. I'm ignoring the input for the randomized algorithm. So all I do is I take a sample from X, pass it through this extractor, and then whatever was the output of the extractor, I feed that into A, and then answer according to this. Now we know that this differs by at most epsilon from the ideal setting. Yeah. So this basically gives us a way of formalizing that okay, we can also work with these these extractors. Now I have no idea if the random number generators that are used in compute in standard machines, etc. I don't even know what this function is. It's typically just they just do some bunch of stuff and then they just say what we did was so crazy. Why should that be introducing some sort of correlation per se? But this is a more formal way of saying that if you knew that that was an extractor, then here is a specific way in which you could build close to uniform random bits. Okay, and that's okay. So now for the next some time, what we are going to do is we're going to try and make precise what these impure sources mean. And we will do this by first constructing, by just coming up with examples and say, okay, this seems to be impure. This seems to be like an impure source or something. And try and somehow use those examples to lead us into a definition. Okay. So the first sort of, in some sense, the first example to think of is probably what are called these IID bit sources. And often people write like a parameter delta to mean, because the definition naturally has one such parameter, which is just basically they are IID bits, except the bits are not uniform. That is, each bit is, think of it as it's like a biased coin where it turns up heads with probability delta. Okay, and of course, if delta was equal to half, then we are talking about normal uniform random bits anyway. But if delta is not half, inherently this is not really a purely uniform random stream. But obviously, there is some amount of randomness in this system that we should be able to use for our algorithms. Okay. Okay. So this is one example. Now let's ask ourselves: can we build extractors for them? So I think last time Sushant mentioned the von Neumann way of looking at these extractors. So von Neumann basically said the following: we'll split the input stream into pairs. Okay, these are all of length 2. And whenever we see a 0, 1, we will return a 0. When we see a 1, 0, we will return a 1. But if we see 0, 0 or 1, 1, we'll just skip. Okay, that is go through the sequence that we got, and just in each block of length 2 or something, if it happens to be a 0, 1, then you return 0. If it happens to be a 1, 0, you return this. But if it happens to be one of these two other things, you just say, okay, fine, I don't know what to return here, I'll just skip. Okay. And the important thing to note is that this actually outputs unbiased bits. Okay, so because the probability of you seeing a 0, 1 versus a 1, 0, the probabilities are the same. So conditioned on the fact that I'm only outputting when one of these two situations happen, since both of them are equally likely, each such output is going to be like a pure uniform random. Okay. Now there's the next question of how many bits will be output on average. I mean, ideally in an extractor, we would like the output length to be a fixed thing. But for now, let's just say that, I just want to get a sense of if I do this process, if I just perform this procedure, how many bits will I output? So what's the chance of us seeing one of these two strings? So that's going to be, what is it? It's going to be 2 delta into 1 minus delta. So roughly every 1 by 2 delta into 1 minus delta many times, I will, on expectation, this many trials is what I need to get into one of these two situations. And when that happens, I output a bit. So the total number of bits outputted is roughly this. Okay, on expectation, of course. So on expectation, you roughly output something like n over some. Sorry, what did I mess up? Okay. Sorry, this is a number. No, this is fine. Yeah. So roughly this, I need this many such bits in order to output one bit, and I have that. So that's the total number of outputs. Total number of output bits I'll be able to output. But the cool thing here is that you actually get, there's no epsilon with respect to how close to uniform you are, etc. Whatever you output is actually like the completely unbiased random bits. Okay, so great. So in this particular sequence, we have an extractor, even if the length of the output is not fixed, but there is a minor like Markov type stuff that you can do to make sure that you output a fixed number of random bits, something which I'm not going to go too much into details because we'll come up with extractors in full generality. Sushant, you had a question?
You say delta is very close to 0, right?
Sorry?
If delta is very close to 0, then it is a perfectly biased coin, right? So you can never hope to
So the point is, I'm thinking of delta as being close to 0, but maybe a constant, say. Like think of delta as something like 0.01 or something. And often my parameter n is the one that's growing.
Okay.
So delta could be a very small constant, but this thing basically says you will still be able to extract a constant fraction of them. Yeah, but your point is right. If delta is much smaller, there should be this question of how many bits can I even hope to extract? I mean, in some sense, even though we have not made precise, we somehow want to say there's only certain amount of randomness in the system. I mean, I shouldn't be able to extract more than that. And we will make it precise once we quantify what we mean by this. I mean, as you might all expect, it must have something to do with entropy. Right? So depending on that is what we want to expect. Okay, good. So this is example 1, which is a very simple example. Here is example 2, which is very related to this, but it's an example just to make sure that the previous construction does not work. Okay, so it's more or less, I mean, to sort of try and force us into coming up with cleverer and cleverer constructions. Okay, we'll just call, instead of saying IID bits or independent identically distributed bits, I'm only going to call them independent bits. So what this says is that, okay, there is still a parameter delta, which is some sort of telling us that every bit is providing some amount of randomness. Okay, but All I'm telling you is that the ith bit, it takes probably, I mean, it is 1 with probability somewhere between delta and 1 minus delta. So again, think of delta as something like 0.01, but I don't precisely tell you what is the probability of it being equal to 1. So the previous construction of 0, 1 versus 1, 0 will no longer work, because 0, 1 and 1, 0 need not even have the same, I mean, the same probability of showing up. Because the first bit and the second bit could have slightly different actual values of probability x equal to 1. Okay. And so in this case, okay, can someone come up with a candidate extractor?
So I can get close to pure. But
yeah, then let's say we settle for that. I mean, that's okay.
So let's say n equals 2 for the moment.
Uh-huh.
So just pick a 4 regular graph, which is mixing. I mean, the random walk on it, meaning it has an odd cycle.
Okay.
Just pick such a 4 regular graph, and now we will just so pick a vertex. So there are 4 edges coming out of it.
So what is the vertex that you pick up first?
No, I'm saying I want to weight this graph so that I can do a weighted random walk.
No, but I am not allowed to feed in any extra randomness into the system, right? I'm only allowed to use the x1 through xn that has been provided to me.
Yeah, I will not use. So I will say you start with any fixed vertex and then you do a random walk. It will ultimately become, I mean, the distribution will ultimately be the stationary distribution, which is uniform, provided I weight the graph properly.
Okay. So yeah, I guess this is very similar to what I think we had roughly the same discussion in the last class when we had a slightly different. Yeah. So in fact, okay, let me instead then do the other thing that we discussed in the last class, which is that I just take these n bits, I'll break it up into some blocks, and in each block I'll just take the parity of all the blocks. Okay, because this is now like, it's like we are thinking of it, I don't know, like a Markov chain in just 2 states or something of that sort. We are using the coordinates itself to move on the Markov chain. So that's one way of describing this. Or another way was that last time we said that, if I have a biased coin, and if I toss it a few times and look at the parity of the number of heads that I get, it becomes exponentially close to half. I mean, the probability of seeing a 1 becomes exponentially close to half. So we can do something of this sort. It's just a question of, how large should this block be? But you can imagine that this block is going to be some function of this delta. Depending on whatever delta is, it's going to be some function of delta, which is some constant which is a function of delta. So the extractor is basically just parity on each of these blocks. Okay. So I guess this is just one instantiation of what you were suggesting. Wasn't that right, Abhishek?
So I think, wouldn't this give you pure random, and isn't that what happened the last time?
No. So last time all we could say was that the probability of seeing a heads here was something that looked like half plus something like, I don't remember, maybe 2 delta minus 1 to the
you're
k.
Right, you're right. Sorry.
So we just need to make sure that this guy is small enough so that it doesn't, I mean, like it's at most epsilon by whatever was the number of things.
Yeah.
So if you set up your k such that this is small enough, then what you're going to end up getting is going to be like close to uniform random bits.
Yeah. So, I mean, I would say my construction was different, but yeah, I also get some close to uniform.
Okay. So good. So let me just write this as a proposition. You can verify this and make sure that this works. Is that this basically says fix any delta greater than 0. And you can choose your n and m as long as, I mean, n and m, but depending on n and m, I mean, I have some guarantees on what epsilon is going to be. Okay. Then there is a polynomial time function that takes n random bits and outputs, or rather n bits coming from this independent bits delta. I mean, it takes it's an extractor for this source. But the error is going to be something that looks like m times 2 to the minus omega n over n. So the m times comes from the fact that there is some error in the first bit, second bit, etc., that you add up. And the error in each bit is going to be something like 2 to the minus omega n over n. Now, obviously, this will make sense only when m is like smaller than n. Otherwise, this number is bigger than 1. Then there's just no guarantee. Okay, but it at least tells you that, okay, if you tell me that I have independent bits delta and I am interested in a guarantee of some epsilon, then you can choose your M suitably such that this works out. If you want that close to uniform random bits, well, okay, I can extract out a certain number of random bits, and we'll have to get a sense of, is that optimal? Can we hope to do better, etc. Okay, so I hope the rough structure is clear for what extractors are supposed to achieve. Okay, and I do want to stress a point here, which will become quite important soon, but I just want to stress it a little earlier than I probably should, just so that uh, that you don't make certain assumptions otherwise. Okay, which I'll get back to this point at a later point, which is that the crucial thing here is that, unlike many other instances that you might have in mind, here notice that I only have access to a single sample of X, and I'm somehow trying to extract randomness from that sample. Okay, so it's not like I can hit this button a few times and then make a certain informed choice on what to output. Okay, so it's like a one-shot sort of system, which is why, like, I don't know, typical sort of arguments in information theory often don't work here, because many times in information theory you're talking about asymptotics in some sense, like what happens when you have, when you average out over many samples or something. Here I only have access to one sample, and I'm trying to output some random bits based on that. So this is the definition has this feature, so which is important to keep this in mind. Okay, and now I'll define these things called unpredictable bit sources. These were introduced by Mikulosh Santa and Umesh Vazirani, and it's a pretty interesting source, which is, it just says the following, which is that it's some source with something like a next bit unpredictability property. Okay, roughly what it says is the following: fix any prefix that you want, like the choices of random bits of the first I minus one of them. Now, even if you condition on all of them and ask what is the probability of xi being equal to 1, that is the ith bit equal to 1, there is some unpredictability in that. It says that, this probability is again sandwiched between delta and 1 minus delta. Like, it's saying that, even if I completely tell you what the prefix is, you still have some sort of uncertainty about what the next bit is going to be. So in some sense, every bit is giving you a little amount of randomness at least. Okay. So these are called unpredictable bit sources. I hope the definition for these unpredictable bit sources are clear. Okay. Now let's ask ourselves. So can someone come up with a suitable candidate for an extractor? In fact, let's make life a little simple. Let's just try to extract one bit. One close to random bit. Okay, let's just maybe try out something. So suppose I did the following. So extractor of x1 through xn, suppose this was equal to just the parity of xi's. Okay, so can this be an extractor, or does someone have a counterexample? So, or rather, so let's say that, if this is not an extractor, then it basically means that you can come up with a suitable Santa Vazirani source such that the output of this extractor is sort of very close to 1 or 0. Again, I'm thinking of delta as being something like 0.01. Think of it as a very small constant.
Yeah, so we can couple them so that the nth one is the
right. So you basically set up such that you set up the nth guy such that the probability of you seeing the parity that makes this equal to 1 is as high as possible or something. Okay, I mean, I hope this, so basically set up. So the answer is no, this is not an extractor. Set up such that xn equals the parity of, let's say, x1, xi from I equals 1 through n minus 1 with probability something like 1 minus delta. So, I mean, there is still like some amount of randomness in every coordinate, but this will ensure that this parity is going to be 0 with probability at least 1 minus delta. So it's going to be a very, very like biased output. Okay, the other candidates we can think of, I don't know. I mean, suppose I did something like majority. I mean, this can just be really, really bad because you could just be that each xi is like a random coin with probability 75% or something, and you're just going to majority is going to completely return 1 most of the time just because of Chernoff. So none of these seem to work. Okay.
I have a question. So regarding the definition of this this thing, so for a small delta, so if delta is small, what would you like to say, that it is more unpredictable, or is it less unpredictable?
So I mean, if delta is too small, then it is somehow less unpredictable in the sense that, I mean, for all I know, it could be the case that this is equal to delta. So I mean, there may be sources where the unpredictability is far less, but of course, a completely uniform thing is also a unpredictable delta. Whatever, that's also a stream like this, but this is a much larger class of streams which include things that I would think of as containing less randomness in them. I don't know if I'm making sense. So
yeah, this contains something which is very, very less random also.
That's right. So, but when we are constructing extractors, we want to work for this entire class of sources.
Okay.
So for all we know, somebody could provide one of these bad sources or something, and I want to be able to work even with them. So that's yeah.
Okay. Yeah.
Okay. So, and we can try out various other things, but unfortunately, we are destined to fail because of the following proposition. And in fact, you will see this in problem set 4, which is a bit bizarre to say because I have not even given you problem set 3, but I'm hoping that we'll give it in the next couple of days. But here's the thing, which is that, you know, just like what happened in the parity situation, which is that there was always a way to set up such that the output of the extractor was super biased. Well, you can actually do this for any function. So this basically says that, you know, okay, fix a number n and a delta, I mean, of your choice. N is the number of the length of the stream that you have, the source that you have, and delta is the unpredictability parameter for the Saptharishi source. And now suppose someone tells you that, oh, by the way, I have an extractor function, and this is my function, which outputs 1 random bit. Then given such a function, you can actually construct a source where the output of the extractor is either very, very close to 0 or very, very close to 1. Okay, so there's nothing like really fancy about us failing in the parity situation. In fact, we will fail in like every situation. Okay, so just in words, this is saying that there are no deterministic extractors. Okay, I mean, I'm sort of telegraphing some move that I'm going to do soon, which is that we're going to slightly change our definition of what extractors are. And then suddenly those sort of extractors will exist. But at least the definition that we have come up with right now, these extractors don't exist because Saptharishi source seems to be a very natural source. I mean, one would say that there is a good amount of randomness present in them, but it seems like these sources, I mean, like you just can't hope to extract random bits from this. Because I mean, like, there is enough richness in the source to fight against any possible extractor construction you could come up. Okay. So, okay, so that's bad news for the moment. But okay, before we go into how we can change our definition, etc., let's try to quantify the notion of what do we mean by weak sources, weak or impure sources, so that it will make it easier when we later quantify this, so that we get a sense of what we can or cannot do. Okay. And normally, whenever we talk about sources that are weak, and I mean, like, they're not really completely random sources, they're impure sources or something, often people talk about the Shannon entropy for this. Okay. So Shannon entropy is just it's a definition that looks like this. It's an extremely important, it's an extremely important concept to know when it comes to almost anything to do with communication or even counting, basically. Okay, it just shows up at so many places. And I mean, definition wise, it's basically look at the expectation of log 1 over the probability. Okay, where the expectation is over x. If you expand it out, this is what you end up with. At the moment, it just feels like some weird expression, but it's sort of quite fundamental. Okay, and as I mentioned earlier, this is great, but it was sort of meant to understand sort of behavior on average. Okay, so there's a lot of asymptotics involved here. I have a feeling there is a P somewhere here which I'm missing. Maybe there's
after M.
Yeah. Okay. Yeah. So yeah, but so the thing is, Shannon entropy will turn out that it's not the right sort of thing to look at when it comes to these extractors, and I'll try and justify this in a short bit. But there are two other definitions of entropy. There are two other variants of entropy, which will be something that we study more. And in fact, one of them is what we'll study a lot more. One is called what is called the Renyi entropy, which is something to do with the collision probability. That is, if you pick up two samples, x and y, what's the probability that x equal to y? Okay, and intuitively, if your distribution is a lot more random, the chance of you seeing this must be very less. I mean, the chance of colliding is far less, roughly. I mean, that's the rough intuition. And the Renyi entropy, which is often defined as H2, or rather, we will be referring to it as H2 because the Shannon entropy, I don't want there to be a confusion with Shannon entropy. It's just the log of the inverse of the collision probability. That's what is going to be the Renyi entropy. And there's another entropy which is called min entropy. And in fact, this is what we will be studying most of the time. This is the property that we will be working with almost all the time, which is just basically saying among all points in your support, that is places where your distribution, I mean, you take this value with probability, non-zero probability, just look at the log of 1 by the probability and take the minimum amongst those. Okay, so in some sense, saying that h infinity of a certain distribution is equal to k is like saying probability that x equal to x is at most 2 to the minus k for all x. That is, no point shows up with too much mass. Like the largest probability that you will ever see in your support is at most 2 to the minus k. That's another way of thinking about what min entropy is.
So in Renyi entropy, what is the joint distribution between x1 and x2?
Oh, so this is an independent. X1 and x2 is on x cross x.
Oh.
Yeah. So you just pick two samples independently and ask what is the probability that these two samples are the same. Yeah. So
okay.
It's just that. Okay. Okay. So to get a better sense, so let me just maybe start off with some basic properties of all of these entropies. And then talk about them separately, which is that first thing is that all of these numbers, even though they might look like they involve weird logs, but obviously there's a log of 1 by a probability. So it'll be a number greater than 1. So this thing is clear that h of x will always be greater than or equal to 0 for all of these definitions that we have. And in fact, it is equality only when x has singleton support. That is, as long as there are two possible different samples you could get, the entropy, any of these entropies will always be strictly greater than 0. So it'll be 0 only if basically X is completely supported on one thing. I mean, there's no randomness there. It's just giving you one. Okay. And another thing is like all of them satisfy that if X happens to be a uniform distribution on some smaller subset, let's say some subset of size 2 to the k, on some one of these subsets, then all of these entropies turn out to be equal to k, which in some sense feels like something that should make sense. I mean, yeah, that like it feels like this is a natural thing that we would want if we mentally want entropy to capture how many random bits are present here. If at the end of the day you're going to give me a uniform random sample from 2 to the k elements, well, there must be k random bits, and all of them satisfy this property. Okay. And the other thing is this additivity, which is that if X and Y are independent, then the entropy of the joint distribution, I mean, where it's just the pair, I mean, like where the two coordinates are independent, is just the sum of the two entropies. So all of these nice properties that you will expect from some measure of how many random bits are present in the system, all of these three definitions satisfy that, satisfy those basic properties. Okay. But it turns out that for every distribution, it so turns out that the Shannon entropy is the largest of the three. And Renyi entropy is somewhere sandwiched between, and min entropy is the smallest of it. Okay. So let's take an example to just get a sense of what are these three numbers going to look like or something. And let's take the following example, which is that here is a distribution with probability 0.99, it just outputs the all zeros. Okay. And with the remaining probability, it will actually output a uniformly random string. Okay. Now let's ask ourselves, what can we say about the Shannon entropy of X? Okay. This is a weird calculation, but I mean, but it just from the contribution of this part alone, it's sort of, I mean, I let you, I mean, just take my word for it that the Shannon entropy turns out to be something like omega n. Okay, some constant times n. I don't know, maybe like 0.01 n or something. Roughly 0.01. I mean, intuitively speaking, because there is a good amount of randomness in the system, because at some point I will be getting like a uniformly random string. It's just that I might have to wait for 100 such samples in order to get one such good sample. And that sample is like a uniformly random string. So it makes sense that I must have a good amount of randomness. But on the other hand, what can you say about H infinity of X? So notice that H infinity of X has something to do with what is the largest probability that you end up seeing. Okay, and the largest probability I end up seeing is actually 0 to the n. It's 0.99 plus a little bit more. Let's even ignore that little bit more. That already tells you that this is roughly equal to log of 1 by 0.9. Okay, which in fact is like what? It's like at most 2 or something. Some really small number. It's some constant. Okay, and the same thing with Renyi entropy also. Okay, this is going to be roughly log of 1 by 0.99 squared, because if this happens so likely, then if I pick up two such samples, well, there is at least a 0.99 squared of seeing a collision. There's probably more here, but it's like this is like a good enough thing. This is also again some constant. So notice that the Shannon entropy is like significantly larger than the Renyi entropy, the min entropy or the Renyi entropy. Okay. So now to convince yourself that, you know, one shouldn't be able to extract randomness from this source. How do I somehow tell you that I can't do this? Well, okay, so the notice that how can I get even 1 bit of randomness from a single sample. Okay, so hopefully this sort of this random variable gives you a sense of why it makes sense to sort of say that Shannon entropy is perhaps not the right value to get a sense of how much of randomness is present in the system, because in the Shannon entropy sense there is a lot of randomness present in the system. But if all I'm allowed to do is take one sample from this whatever distribution, well, with probability 99% chance or something, I'm going to end up with this one constant string, 0 to the n. How can I possibly hope to extract anything from it? So just because of the fact that the output is so, there is a big spike at 0 to the n. Well, no matter what function I end up writing after this, I mean, there'll be one value that takes probability at least 0.99. So the fact that there was a uniform distribution with chance 0.01 somehow seems irrelevant when it comes to the fact that you're only working with one sample. Okay, so I hope this roughly gives you a sense of why Shannon entropy is perhaps not what we should be looking at when it comes to randomness extractors, where all we have to work with is one sample. Okay, so what we'll instead be doing is working with these two, and in fact, we will mostly be working with min entropy. Okay. So are there any questions so far? I mean,
yeah, so this data processing inequality also happens for Shannon, I know that much.
Yeah, I have a feeling it also happens here. I mean, it should. Yeah, there should be an analogous data processing inequality in these things. I have to verify. I mean, I'm saying this only because these all seem to be natural definitions of entropy, and the data processing inequality seems like a natural ask. So I suppose it should be satisfied. Yeah.
Yeah. So I mean, that is one explanation. Could be one explanation why, if you had just, suppose you want to produce one bit, then you're certainly decreasing the entropy, whatever this was.
Yeah. Yeah.
So if you were close to uniform, you would have at least some entropy, like log 2, which is one bit of.
Okay. Okay.
But you start with 0.01 n, so
yeah. Okay. So that's also.
Yeah. Okay.
Okay, but at least it sort of tells you that I mean, Shannon entropy does not seem to be the most natural thing in this context, even though it's absolutely essential in context where you're dealing about something happening like many times, and you're looking at an average and asymptotic sort of behavior. But here you have one sample, and you have to make do with one sample. So it turns out min entropy seems to be the better notion to work with. And that's what we'll work with. And in fact, we will just call these, we'll refer to them as K sources or weak K sources to just indicate that we are dealing with a distribution where the min entropy is at least K. Okay. And as I mentioned earlier, min entropy is just saying that no value takes probability. I mean, you never get a value that is too likely. Like any sample that you have, there's at most a 1 over 2 to the k chance of you receiving any particular sample. And that k is what this min entropy parameter is. Okay. And I will let you check that all of the previous examples that we saw, these independent bits or the Santavajinani source, etc., the min entropy itself is about omega n. The constant might have a parameter delta along with it, but it's basically there is a linear number of random bits in all of them. So they're all in some sense, even from the context of min entropy, they are sources that have an abundant amount of randomness. And I sort of, I would definitely want to get like access to random bits from there. Okay. So here are some other examples of sources, sort of weak sources. They're quite interesting examples. The first one is what are called bit fixing sources, which is basically saying that some among these n bits, some k of them are completely random. Like they're all uniform, they're independently taking values 0s and 1s. But all other n minus k bits are always fixed. It's just that we may not know what the location of those k bits are, or what the other n minus k bits are fixed to. Okay, So it's just, I don't know, pictorially, it's something like this, where there's some bunch of stars. There's at least k stars in them. The rest are fixed to some 0, 1, 1, 0, 1. The rest are fixed to some specific values, but the stars can be anything. And every time I ask for a sample, the stars might be assigned, but the rest are fixed. And as you can imagine, no particular string takes probability more than 1 by 2 to the k. So these are certainly sort of sources. I mean, like these are certainly k sources. Okay, so this is one such example. The other example is a slightly more sinister version of the same thing, which is that these are called adaptive bit fixing sources, which is that you first set the stars and then you set all the other bits as some specific function on these things. So it's not even that the other bits stay the same throughout. It's just that the data only contains k bits. The rest of them are some weird functions of these k bits. Okay, but yeah, but that's what is called an adaptive bit fixing source. And again, here notice that these must be sources with min entropy at least k, as long as I have at least k stars in them. Okay, so I hope these two are clear. And here is another definition, which are called flat k sources. And this will be very important because it sort of really captures the notion of min entropy, which is that just think of a uniform distribution on some unknown set of size 2 to the k. Okay, there is some set of size 2 to the k, it's some distribution on those, that's it. And it's a uniform distribution on those, but you just don't know what this subset is. And these flat k sources are very important when it comes to min entropy, because it turns out that any source of min entropy is basically a convex combination of these flat k sources. Okay, this is a simple exercise, but I'm just going to take this for granted. But if you're really interested in a proof, I think Vadan's notes has two different proofs of this fact. There's one which is more geometric and the other which is more hands-on. But basically the point is, whenever you think of min entropy, basically tell yourself it's essentially a flat k source with some small bells and whistles attached to it. And mostly if you come up with an extractor for flat k sources, that's already good enough for min entropy, because any other source is just a convex combination of these. So you will end up working for any of these other k sources. Okay, so let me maybe pause here for a minute to just get a sense of, are people following? Like, are there any questions?
In a flat k source, k is the variable, right? You don't know what is k.
Yeah, no, often in many of these instances, I might give you a guarantee on what k is. That is, I will tell you that, okay, I will give you a flat 100 source. Okay, technically speaking, flat 100 source means that it's a source on exactly 2 power 100. It's a uniform distribution on 2 power 100.
Yes.
But I may not tell you what those 2 power 100 strings are. Yeah, so all I'm telling you is that, there is some randomness in it, in the sense that it will give you a uniform random sample from a smaller support.
Okay.
But I won't tell you what the support is.
Okay.
And you have to construct an extractor irrespective of what the support may be.
Okay. So there's a larger sample space, but most of it is useless. Like,
yeah, most of it, those you'll never get samples from those.
Okay.
So there's just there's this big space of 2 power n strings, but inside that there is some space of size 2 power k, and this random variable only gives you a random sample from here. Yeah, so that's what a flat k source looks like. Okay, and it so turns out that every k source, where by k source I mean it's like a min entropy guarantee, you might as well assume that it's a flat k source, in the sense that because every k source is a convex combination of these flat k sources. And because of that, I mean, mostly what will happen is, if your extractor works for flat k sources, like if your extractor works for all flat k sources, it will also work for convex combination of sources that you have, and therefore it will work for all k sources. Okay, now some of you may be wondering, saying, why the hell are we doing all of this, like going into details about what these sources are, etc., when we know that extractors don't work? I mean, like even for Santa Vazirani sources, we can't construct extractors. And here is where I want to say that we only know that deterministic extractors don't work. Okay. And so we are going to slightly change the definition a little bit. But before I do this, let's, give a sense of how badly these extractors don't work from the context of, let's say, K sources. Now that we have a name for it. So here is a weird proposition, which is that fix any potential extractor function you have. It's something that takes n bits and returns a single bit. Then there is an n-1 source on which this extractor is always a constant. Okay. So in terms of min entropy, the amount of randomness present in it is huge. There are n-1 random bits in some sense. But this extractor output will always be constant. Now, once you see the statement, there's only one thing you can try, which is basically just take your source to be the uniform distribution on either the pre-image of 0 or the pre-image of 1. One of these two must be at least as large as 2 power n-1 or something. Okay. And just by definition, X is now a distribution. It's a uniform distribution on at least 2 power n-1 points. So the min entropy is at least n-1. And again, by definition, the extractor on this source is always going to be a constant. And it's just a whatever. We had a slightly different version, which I said I will give in the problem set. But if you're okay with just dealing with K sources or something, this gives an absolutely trivial argument to say that, if I'm allowed to pick up a K source, an n-1 source, then I can just kill any deterministic extractor. You give me a deterministic extractor, I will find a suitable K source on which this extractor is just a constant. So it fails as badly as you could ask for. Okay. But so what we are going to do instead is slightly modify our definition and start talking about what are called seeded extractors. Okay. And so fortunately, it'll turn out that seeded extractors do exist. And that's what we'll focus on in the module. Okay, so what is a seeded extractor? A seeded extractor now not only takes a single, a sample from a source, it takes a short seed, which is expected to be truly uniform. Okay, but think of S as a very short seed. I mean, we'll soon see the usefulness of this, but that's what it is. Now this extractor takes two coordinates as input, which is a sample from your potential weak source and some short seed, and then outputs close to random bits. And we will say that such a function is a k comma epsilon seeded extractor if for every k source x that you could think of, the output of the extractor when you feed in x and the uniform distribution on the seed, that must have total variation distance at most epsilon with the uniform distribution on m bits. Okay, so I hope the definition is clear. So it's the same thing as earlier, except that we are pumping in a little bit of randomness. We are adding a little bit of extra randomness and then saying that, okay, then once you have this little bit of extra randomness, I should be able to output something that looks as close to uniform as possible. Okay. I think it is fair for you to ask, we are basically saying that there is no notion of pure randomness. It's very hard to get that. We only have impure sources, etc. And now I'm asking you to pump in like truly uniform random bits, but just wait for a little bit and we'll try and clear that out. But just to get a sense of what are the sort of parameters we want to keep in mind. The ideal situation would be when the number of bits I'm outputting is basically the amount of randomness that was pumped into the system. So how much randomness was pumped into the system? Well, this was a source on n bits, but it has only min entropy k for all I know. So there's basically just k random bits coming from these first n bits. So there are k bits of randomness here, plus I additionally pumped in some s bits of randomness here. So I would ideally like m to be equal to k plus s. Or maybe I lose a little bit, but roughly equal to k plus s. That should be the goal. And hopefully it works for k being very small also. Like even if you just promise to me that, look, I have a source that's a really, really weak source. Like the amount of the min entropy that's present in the source is like quite bad. But irrespective of that, can you still extract randomness? And hopefully we should still be able to extract that randomness. And of course, we would want this to be efficient. Okay. So is the definition of seeded extractors clear? If there are any questions, we'll take those.
I'm a bit confused why you want k to be as small as possible, because then m is approximately equal to s, right? So then you can just read the uniform
No, in
seed
the
and
sense that, okay, actually, that's a good point. So ideally, when I mean k to be as small as possible, maybe, okay, let's fix some specific parameters. Suppose k was equal to something like, I don't know, root m. Okay. And let's say s was something like, I don't know, log n or polylog n or something. I still want to be able to recover about root n plus polylog n many random times. So that is what I mean is I want the extractor to be able to be functional even for very, very weak random sources. That's one thing. And I would also want the extractor to be able to extract as many random bits as it possibly can. But you're right. I think the setup will make sense only when k, like s is like much smaller than k.
yeah.
That is the extra random bits I'm feeding into the system. Hopefully, it's like really minuscule amount. In fact, we will soon see that it'll be so minuscule that we can actually afford to brute force over it. So that's going to be the focus of things. But k, maybe it's like root n or something like that, or n to the 1/100 or something like that. Yeah. So this is what seeded extractors are. And yeah, okay, good. So this is what we would want in an ideal situation. So anytime we come up with a definition of this sort, it should hopefully immediately make you think of, do such extractors exist? Okay. I mean, earlier we made the mistake of not doing that first. We started off by saying we'll came up with a definition, and then realized that such definitions just don't exist. But fortunately, seeded extractors do exist, and in fact, so like what we have done earlier, we'll try to get a sense of what is the ideal parameter setting. Okay, and we'll do this by basically saying, let's just pick this extractor function at random and ask ourselves, for what sort of parameters is this random function going to give us what we want? Okay, and it will turn out that if you choose your seed length to be roughly log n plus log 1 over epsilon. Okay, that's, I mean, this is just some ugly expression, but just think of it as like it's basically order log n plus log 1 over epsilon. Okay, then you can actually extract more or less k plus s bits of randomness. You lose a little bit, but hopefully when epsilon is a constant or something, this little bit is not much. Okay, and for that particular s and that particular m, a random function of the form 0,1 to the n cross 0,1 to the s to 0,1 to the m happens to be a k comma epsilon extractor with very high probability. Okay, and that tells us that not only do extractors exist, once you set up the right setting of parameters, extractors exist in plenty. So it's again, we are in this finding hay in a haystack sort of situation, that there are lots and lots and lots of extractors. What we want to do is get our hands on something which is efficient, get our hands on one of these. Okay, so I'm going to give an overview of the proof just to give a sense of what the structure of the proof is. And the moment it gets to a calculation, I'm going to stop and say that, plug in the parameters and it will work. Because I mean, the calculation is really not, I don't know if it's really insightful, but hopefully you should get a sense of at least how do you go about proving something of this sort. Okay. Now, like I mentioned last time, suffices to show it works for flat sources. Flat k sources. because any min entropy K source is a convex combination of these flat sources. So I mean, an extractor that works for flat K sources will also work for all convex combinations of them. So we are done. So what we'll do is let's fix a source X. Okay. And what does it mean to say an extractor fails? Extractor fails. So what does this mean? This means that the output of the extractor is not within epsilon of the uniform distribution. Okay. What was one way of certifying that the output is different from the uniform distribution? One possible certificate is some event such that the probability of the event happening here versus the probability of the event happening here differs by at least an epsilon. Okay, so that's the same thing as saying that there exists an event. Let me just call this a T. An event is just a subset of the output space. Okay, such that probability that the extractor output X comma US in T minus the size of T by 2 power n. This is what would have happened in the truly random setting. Okay, this difference is at least epsilon. Okay, it's just I'm just writing down the definition of what it means to say that the total variation distance is different. Well, the total variation difference being greater than epsilon means that some event like witnesses the fact that one of them is taking, I mean, the event is satisfied more in one as compared to the other. Okay, now, so what is the output of an extractor when I pick ext at random? It's going to be some uniform string in 0, 1 to the n, right? Like, what does it mean to say we pick this function at random? That is, for every input, I just assign a uniformly random output as the value of this extractor. Okay, which means the probability over extractor that ext fails on X with respect to the test T. Okay, this is, I mean, this is basically Chernov's bound. Okay, I mean, it's just saying that, I mean, each of this is going to be one particular sample from 0, 1 to the n. Because if I pick this function extractor at random, that's what I would be doing. And we are asking, among these inputs, how many of those samples fall inside the set T? And this is like the deviation from the uniform distribution. And this is at most 2 power minus omega. How many random bits do I have? So X is some K source. So there are 2 power K random strings. And there are S random bits here. So this is going to be 2 power K plus S times epsilon squared. Sushant, did you have a question?
No.
Okay. So this is the probability of the extractor failing on one particular K source and one particular test. Okay. But fortunately, this number is so small that we can afford to take a union bound over all of them. Okay. So this implies that probability over the choice of the extractor, that extractor fails for some X and T. Okay. So this is at most this number times how many different K sources do I possibly have? Well, I have 2 power n strings overall, and a K source means that I need to pick up some 2 power K strings among them. So therefore, the number of such K sources is like 2 power n divided by, 2 power n choose 2 power K. That's the number of different K sources I'm fighting against. Okay, how many different tests do I have? Each test is some subset of 0, 1 to the n. So this is some universe of size 2 power n. And I need to fight against all possible subsets of these universe. So that is something like 2 power 2 power n. Okay, and times this 2 power minus omega 2 power K plus S epsilon squared. Okay, and now I'm going to basically wave hands and say that for the choice of parameters in the statement. Okay, whatever the RHS is like way smaller than 1. Okay, just I mean like, okay, here is a rough calculation. There is a 2 power m here. They will, I mean, this will involve a 2 power k here, because like the exponent will show up here. So let's look at the exponent. There's a 2 power m, there's a 2 power k, and here you're fighting against 2 power k plus s. And that should hopefully tell you that if m and k satisfy this particular property, then fortunately this part is so small compared to how large this is that these things are not going to really hurt you. It's some stupid calculation which I'm not going to do. So this implies that exp is indeed an extractor with high probability. So it not only tells you that extractors exist, it tells you that extractors exist with very, very high probability, as long as the parameters are reasonable. So which also seems to make sense, which is that the amount of randomness that was being pumped into the system was k plus s. And we are asking to extract a little bit less than how much was pumped into the system, which is quite fine. And secondly, s seems to be so small. S is just logarithmic in the parameters involved. So hopefully it's not, I mean, like asking for fresh randomness of s bits is hopefully not too much to ask for. Maybe that is like fine. Okay, so I mean, this is a hand wavy thing mostly to tell you that seeded extractors with seed length about order log n do exist. And therefore, obviously, the next few lectures, what we are going to try and ask for is like, can we construct them using what we have seen so far? Okay. Now, finally, we started off this entire lecture by saying that the reason we want to do these extractor constructions is because we are trying to simulate randomized algorithms, which was relying on uniform random bits. Okay. But now suppose, let's say that, I give you access to a source X. Okay, this is a weak source. I don't know, weak K source. And I give you access to a seeded extractor. 0, 1 to the N, 0, 1 to the S, 0, 1 to the M. So this is a K comma epsilon extractor. And I promised you that this is also efficient. Okay. And there was some randomized algorithm A that needed M random bits. Okay, now how would you simulate the algorithm? So A is a randomized algorithm that needed M pure random bits. Okay. So what would a simulation be here? So what would be one reasonable way to run A given only access to X and this extractor? So previously what we were doing was we were just running the extractor on X. But now I also need to feed in a little bit of pure randomness. Okay. So, but here the amount of pure randomness I'm feeding in is so small that hopefully I can just brute force over it. So what would you want to do? Okay, so one simple thing to try here is basically saying that, suppose you want to run the randomized algorithm on something. First, what you do is the following: you pick a sample X according to whatever is the weak source of randomness. Okay. Now what I'm going to do is I'm just going to run over all possible A on extractor on X and Y. Okay, and just take the majority as a range over all possible strings in 0, 1 to S. I just enumerate over the seed and look at the average behavior of extractor of X when I feed in the uniform distribution, but I'm sort of doing it in a brute force manner because I don't have access to a uniform random bit in 0, 1 to BS, but S is fortunately so small that I can just run over all of them. So, and this basically says is that, I mean, the amount of difference is at most some epsilon, and this is also an efficient simulation. So I hope this rough proposition was clear to just indicate that these seeded extractors are already good enough from the perspective of like using it in the context of randomized algorithms, because if the seed is small enough, then, and that is if 2 power s is not something that is going to hurt your running time too much, then this is something that you can afford to when you're simulating a randomized algorithm using only a weak source. All you have access to is a weak source, and you can basically get roughly the same guarantees that you wanted from it. Okay, so hopefully this was clear. So this at least tells us that the slightly weaker definition that we had of the notion of seeded extractors, I mean, not only does it have the advantage that such seeded extractors do exist, and that we are not trying to build castles in thin air, like these seeded extractors do exist. And second, what we now learn is that these seeded extractors are sufficient for the same application that we had in mind to begin with, which was to make sure that randomized algorithms can still perform only in the presence of weak sources and stuff like that. And yeah, and what we are going to do in the next few lectures is basically try and construct such explicit efficient extractors. And we'll basically be throwing our kitchen sink at it. I mean, like we'll try and figure out, okay, we have seen hash functions. Do hash functions have some extractor-like properties? And then we'll ask, we looked at expander walks. Do expander walks have extractor-like properties? And somewhere in the course, we'll also see, we came up with some constructions of PRGs using hard functions or something. Do those things also give you extractors? And turns out the answer to all of these questions will be yes, except they will all work for slightly different parameter settings. And eventually we'll put them all together to get the extractor, the dream extractor that we wanted, which is for any choice of k that you want, using only logarithmically many random bits, and you extracting almost all of the random bits that was pumped into the system. So that's what we'll eventually do in this module. So yeah, so that's going to be the focus of the next few lectures. And after we are done with this module, basically what we had in mind was whatever lectures are left, we will just pick up some assortment of interesting results in pseudorandomness, not particularly in CS, but in other fields. Maybe something in math or something in physics or whatever, and discuss those, and depending on how much time we have, etc. So that's the plan for the next few lectures. Okay, I'll stop here. By the way, we'll put an announcement on Academy. We won't have a class on Thursday. Thursday is Diwali. There's a holiday. I don't know, for some reason I had forgotten this when we put the schedule out. So we won't have a class on this Thursday. We'll have a class on next Tuesday. And I also mentioned earlier that we'll have our office hours after Diwali because Prahlad appears to be busy until then. So after Diwali, sometime we'll have an office hour, but I'll send a doodle poll for sure today. Okay, so let me stop now and maybe take questions if there are any. Yeah.
So could you go back to the proof of existence of
Yeah.
K. So in the second step of that, the first implication.
This one?
Uh,
Sorry, this one or the next?
yeah.
Okay.
So can you just sort of explain the statement once?
Okay. So let's do the following. So let's basically think of this extractor of k comma s. Okay, this is currently chosen to be a random function. Okay, so which means for each of the points in the domain, a random output string was assigned by this. Right? So when this extractor is picked at random, what is really happening is that you're looking at all possible things in the domain and how many of them are there. So there are basically 2 power k possibilities for whatever was fed into X. Okay, and there are 2 power and then there are 2 power s possibilities of whatever was fed into this uniform distribution. And we are asking what fraction of them fall inside my set T. Is this clear so far?
Yeah.
Okay. So we are basically saying that, I would like this fraction to be size of T by 2 power n. But what is the chance that you deviate from this fraction by a parameter more than epsilon? So another way of stating this is saying somebody gave us 2 power k plus s samples from 0, 1 to the m. And what's the probability that more than, I don't know, I mean, like the fraction of those that fell inside the set T was different from size of T by 2 power m by a parameter more than epsilon. And this is basically Chernov's point. We're just saying we took this many samples and looked at their empirical average. What is the probability of deviation from this being more than epsilon?
When you say probability of extractors, you're picking the extractor at random?
Yeah, I'm picking, or what I mean here is like this. I mean, this just means that this function 0, 1 to the n cross 0, 1 to the s cross 0, 1 to the m, this function itself is picked at random.
Okay.
So I'm just saying that the goal was to construct an extractor. By that, I'm supposed to construct such a function. Let's just pick this function at random among all possible functions. And just ask, what is the chance that we get lucky and it actually happens to be an extractor? So was that okay? Yeah. So yeah, so that's it. So this is roughly what happened. It's just some nasty calculation that needs to happen to eventually convince yourself that it's the right hand side is like strictly like much smaller than that. Okay, so if there are no further questions, then let's meet on next Tuesday. We won't have a class this Thursday. We'll meet on next Tuesday.